All right, in this video, we will be going over section 3.2. In this section, we are going to talk about first derivative and curve sketch. Okay, basically, we are going to use the ideas of derivatives to sketch the graphs of functions. All right, I want to start with this theorem, theorem 3.6. The derivative measures where a function is increasing or decreasing. Okay, here is the statement of the theorem. Let f be a function that is differentiable on an interval I. If f prime is positive in the interior of I, then f is increasing on I. If f prime is negative in the interior of I, then f is decreasing on I. The last part says if f prime is 0 in the interior of I, then f is constant on I. Okay. This theorem, we can easily understand this theorem intuitively using graphs. Okay. So let's try to provide the graph for the first part. Part A. What is the situation where f prime is positive? Well, if you want your f prime to be positive, your graph should look like this. On the interval a comma on the interval I. Let's say your interval I is a comma b. Okay, your interval I, for example, let's say that is a comma b, closed interval. It can be the open interval as well. Okay. All right. So if you want your f prime to be positive in the interior of this interval I, then your graph has to look like this. If your graph looks like this, as you can see, doesn't matter where you draw your tangent to your graph, the slope of that tangent is positive. Everywhere on this graph, the slope of the tangent is positive. That means your f prime is positive. If your f prime is positive in that interval, what is a characteristic of this function? As you can see from the graph of this function, this is an increasing function in that interval. As you can see, your graph is going up. Okay. As x increases, your y also increases. Okay. Or in other words, your graph is going up when x goes from left to right. All right. And let's look at the second part. Let's try to provide an example for the second part. If f prime is negative in the interior of I, then f is decreasing on I. Here is an example. Part B, f prime is negative means you should have a graph like this. Values green, you should have a graph like this. On the interval a comma b. My interval a comma b is what I denote by I. Okay, I is equal to a comma b, either closed interval or the open interval. In that interval, if I want my f prime to be negative, your graph should look like this. As you can see, on this graph, everywhere, the slope of the function f of x is negative, because if you draw the tangent to any point on the graph, that tangent has a negative slope. That means f prime is negative. Okay, so what is the characteristic here? If f prime is negative everywhere on this interval, your function is decreasing. It is going down. Okay. All right. By the way, this is the function y is equal to f of x. Okay. In this case also, this is the graph of the function y is equal to f of x. And then let's look at the third part. If f prime is 0 in the interior of I, then f is constant on I. Your function should look like this. Y is equal to f of x. Then only you will get f prime of 0 everywhere. Okay. You look at this constant function. If you draw a tangent at this point, that tangent is horizontal. If you draw a tangent at this point, again, that tangent is horizontal. Everywhere your tangent is horizontal, that means f prime is 0. If you want your f prime to be 0, that has to be a constant function like this. Okay. All right. That's the geometric interpretation of this theorem. I'm not going to prove all the parts, but let's quickly prove part A. Okay, if f prime is positive in the interior of I, then f is increasing on I. Okay, first of all, what do you mean by an increasing function? When do you say f is increasing? We say that f is increasing if bigger the x value, bigger the y value. Okay, increasing if a less than b, then f of a should be less than f of b. Bigger the x value, bigger the y value. Okay, if this is the case for any two values a and b, then we say that the function is increasing. Okay, that's by the definition that you learn in your pre-calculus class. Function is increasing if for any chosen values a and b, if your a is less than b, then f of a has to be less than f of b. Then we say that function f is increasing. Okay, that's the definition from pre-calculus. I'm going to get rid of this. Okay, so let's prove this one. Okay, here is my hypothesis. F prime is positive in the interior of I. So I will assume that. Assume that f prime is positive on I, in the interior of I. Okay, we are right in the interior of I. Okay, now I'm going to take two values from the interval I. Let a comma b be two values from the interval I with a less than b. Okay, then to show that f is increasing, that's what I want to show. F is increasing on I. To show that f is increasing on I, what I need to show is, all right, must show that f of a is less than f of b. Bigger the x value, bigger the y value. Okay, if a less than b, f of a should be less than f of b. That's what I need to show in order to show that f is increasing on the interval I. All right, how do you show this? How do you show this? Well, I'm going to apply the mean value theorem. Okay, by mean value theorem, there exists some c between a and b such that f of b, pardon me, f prime of c is equal to f of b minus f of a divided by b minus a. Now what you do is you multiply this b minus a to the other side. F prime of c times b minus a is equal to f of b minus f of a. Now notice that f prime of c is positive. That's my hypothesis. I'm assuming that f prime is positive everywhere on the interval I, in the interior of the interval I. But notice that c is in the interior of this interval a comma b. So this is positive. Okay. By the way, a comma b is inside this interval. Okay. So that means c is in the interior of this original interval I. Okay. Notice that this is positive because of my hypothesis. And this is also positive because I'm assuming that b is greater than a. So b minus a is positive. This whole thing is positive. That means this term has to be positive because these two are equal. What does that tell you? That tells you that f of b minus f of a is greater than, pardon me, f of b is greater than f of a. That's what I want. That's what I wanted to prove. I wanted to show that f of b is greater than f of a. We have proven that here. That means if f prime is positive in the interior of I, then f is increasing on I. So that completes the proof of part A, and I will leave the proofs of the other two parts as an exercise for you. Okay, next, before I go to my next example, I want to state a theorem that we discussed previously in section 1.4, theorem 1.19. Okay, a function can change sign only at roots and discontinuities. Okay, here is the statement of the theorem. A function f can change sign from positive to negative or negative to positive at a point x is equal to c only if f of x is 0, undefined, or discontinuous at x is equal to c. Okay, so that's a very important theorem. All right, recalling that theorem, now let's go to our first example. Okay, here is the first example that I want to go over. Use theorem 3.6 to determine intervals on which each of the following functions are increasing or decreasing. My goal is to use this theorem that we just discussed. I know that if f prime is positive, I know that my function is increasing. If f prime is negative, I know that my function is decreasing. So to determine in which interval my function is increasing and in which interval my function is decreasing, all I have to do is I need to check where my f prime is positive, where my f prime is negative. That's what I'm going to do. Okay. To do that, let's work on the first part. To do that, first of all, I'm going to find my f prime. F prime of x is equal to 3x squared. It's clear. That's my f prime of x. Now, I want to know where my f prime of x is positive, where it is negative. How do you determine where f prime is positive and where f prime is negative? Well, from the previous theorem, I know that f prime can change sign at a point x is equal to c only if f of x is 0, undefined, or discontinuous at x is equal to c. Okay, so or in other words, this function can change the sign only at zeros, discontinuities, or points where the function is undefined. But this function is defined everywhere. This is continuous everywhere because this is a polynomial. So that means this can change the sign only at its zeros. So let's find the zeros of this function, derivative function. If you set your f prime x to be 0, you get 3x squared is equal to 0. That means x has to be 0. So that means your function, your f prime of x can change the sign only at x is equal to 0. Now I'm going to go ahead and construct a sign chart. To construct a sign chart, I place my 0 here. That's the only point where your f prime of x can change the sign. If it changes, now I'm going to compute the sign of f prime in each interval. I have two intervals here, right? One interval is minus infinity to 0. The other interval is 0 to plus infinity. Okay. In those two intervals, I'm going to compute the sign of f prime of x. For that, I'm going to pick a number from this interval. I'll pick -1. F prime of -1 is equal to 3. It is clear. If you plug in -1 in this function, you get 3. And then I'm going to pick a number from this interval. I'll pick +1. Then f prime of +1 is equal to 3 again. As you can see, both these numbers are greater than 0. This is greater than 0. This is greater than 0. That means your derivative f prime has to be positive in this interval, and also it has to be positive in this interval. Because you pick up one value from this interval, for that particular value, your f prime is positive. That means your f prime has to be positive for all the values in that interval. That is because your function f prime can change the sign only at x is equal to 0 if it changes the sign. Okay, there is no any other place where it changes the sign. That means your f prime has to be positive in this entire interval. And again, your f prime has to be positive in this entire interval because this number is positive. Okay, so I have the sign chart now. Now, based on this sign chart, using the previous theorem that we learned, what can we conclude? Notice that in this interval, first of all, let me write f prime of x is positive on minus infinity comma 0 open interval, and also we have f prime of x is positive on the interval 0 comma plus infinity. That's what we observe here from this sine chart. Okay, positive, positive. So now by previous theorem, by theorem 3.6, by theorem 3.6, f is increasing on minus infinity comma 0, the closed. I close 0, I include 0 there, and 0 comma infinity, again I include 0, because theorem only requires my f prime to be positive in the interior of that interval. Okay, so I can include this 0 there to determine where it is increasing. Okay, so my function is increasing on this interval and on this interval. What does this mean? My function is increasing from negative infinity all the way up to 0, and then again it is increasing from 0 to positive infinity. 0 is included. That means my function is increasing everywhere. That means f is increasing everywhere. Everywhere means minus infinity to plus infinity. You kind of combine these two. Your function is increasing on this interval and it is increasing on this interval. That means it has to be increasing on this whole interval minus infinity to plus infinity. All right, let's move on to the second part. In the second part, I have g of x is equal to g of x is equal to x squared minus 2x plus 1. All right, how do we determine where it is increasing and where it is decreasing? Again, I'm going to check the sign of g prime. Okay, sign of the derivative. If the sign of the derivative is positive, I know that my function is increasing from the previous theorem. If the sign of g prime is negative, my function is decreasing. So I'm going to construct a sign chart for this function as well. Not for this function, for the derivative of this function. For that, the first thing I do is I'm going to find the derivative. G prime of x is equal to 2x minus 2. Now I want to see where my function is positive and where my function, where my g prime is positive and where my g prime is negative. For that, we know that from this theorem, the function can change the sign only at zeros, undefined points, or discontinuous points. But notice that this is a nice polynomial, so it is continuous. Pardon me, this is a nice polynomial. This is continuous and differentiable everywhere. Okay, so there is no undefined point. There is no point which is that is not continuous. So what I'm going to do is I'm going to find the zeros of this derivative function. G prime of x is equal to 0. That will give you 2x minus 2 is equal to 0. If you solve for x, you will get x is equal to 1. So x is equal to 1 is the only 0. So your function g prime of x can change the sign only at x is equal to 1 if it does. Okay. All right. Now let's construct a sign chart to determine where my f prime is positive, where my f prime is negative. Here is my point x. I mark my 0 of my derivative function, that is x is equal to 1. I mark 1 here, and then I compute. I pick a value from this interval. I'll pick 0 and compute g of 0. You will get g of 0 is minus 2. It's clear. You plug in 0 here, you get minus 2. That is less than 0. That means your derivative has to be negative in this interval. In this interval, minus infinity to 1. Your derivative has to be negative. And now I'm going to pick a value from the right hand side. I'll compute g of 2. Pardon me, g prime. Here g prime, okay? Pardon. I have to construct the sign chart for g prime. So I compute g prime of 2. G prime of 2 is equal to 2. That is positive. That means your derivative has to be positive in this interval. In the interval 1, infinity, your derivative has to be positive. In the interval minus infinity, 1, your derivative has to be negative. Okay, now I have the sign chart. That means this, oh, by the way, from this point onwards, for increasing and decreasing regions, we are using open intervals. Okay, we do not use closed intervals. We are using only open intervals, unless we use closed interval or closed intervals only if it is needed, like in the previous case. In the previous case, we wanted to consider closed intervals like this, closed points. But here onwards, we will be writing only open intervals when we talk about increasing and decreasing intervals. All right, now by the previous theorem that we learned, by theorem 3.6, theorem 3.6, g is decreasing on the interval minus infinity, 1. As I said, we use parentheses from here onwards, okay? And g is increasing on 1, infinity. Again, I'm using parentheses. It is increasing. Why is it increasing? Because my derivative is positive. If the derivative is positive, my function has to be increasing on that interval. Okay. All right. That completes that part. All right. Let's move on to the next example. Here is the next part. Pardon me. We are given h of x is equal to this particular function, and again, we want to determine where this is increasing and where this is decreasing. For that, what we need to do is we need to figure out where the derivative of this function is positive, where the derivative of this function is negative. For that, I'm going to construct a sign chart for my derivative function. Okay. For that, I'm going to have to find the derivative, right? So here is the derivative. I found the derivative. This is going to be your derivative, okay? Please make sure that you try this one and show that this is the derivative, okay? If you find the derivative, you will get h prime of x is equal to x plus 3 times x minus 7 divided by x minus 2 whole thing squared, okay? You should be able to prove that. Now that I have the derivative, I can construct my sign chart. I know that my derivative, h prime of x, can change the sign only at its zeros, discontinuous points, or undefined points. Okay, here, what are the zeros of h prime of x? Let's write zeros of h prime. What are the zeros? How do you find the zeros of this rational function? Well, there are no common factors in the top and bottom which are cancelled. So to find the zeros, you set your top to 0. Okay, basically to find the zeros of this h prime, you set your top to 0. X plus 3 times x minus 7 is equal to 0. That will give you x is equal to minus 3 or x is equal to plus 7. Those are the two zeros of my function h prime of x. And I also need to find the points where this function is not continuous. As you can see, we clearly have an infinite discontinuity at x is equal to 2, right? Because at x is equal to 2, if your x is equal to 2, this is 0. your denominator is 0. So you are going to have a vertical asymptote. That means you have an infinite discontinuity. Okay, discontinuity. Discontinuity of h prime. That is x minus 2 is equal to 0. You set your denominator to 0, this factor to 0. Or you could say x minus 2 squared to 0. That means x is equal to 2. Okay, so these are the points, these are the 3 points where your function h prime of x can change the sign if it does. Okay, now I'm ready to construct the sign chart for this function. To construct my sign chart, I'm going to place these 3 points, -3, 2, and 7. All right, here are my points again. When I place these 3 points on the real line, I have 4 intervals. The first interval is this one. The second interval is this one. This interval means -infinity to -3. Then this is -3 to 2, 2 to 7, and 7 to plus infinity. Now to determine the sign in each interval, sign of h prime. Notice that I'm constructing this sign chart for h prime. To determine the sign of h prime in each interval, I'm going to pick a value from each interval. From this interval, I'm going to pick a value, that is, I'll pick -5. I compute h prime of -5. Notice that all I want is the sign of this number. I don't really need the exact number here. I just need the sign of that number. To determine the sign of that number, I can go to my function h prime of x and plug in -5. If you plug in -5 here, you get a negative number, right? So you put a minus sign here. And if you plug in -5 in the next expression, you get a negative number again. And if you plug in -5 in the bottom, you get a positive number because you have a square there. You have a positive number. So that means if you simplify these signs, in the top you have minus times minus, minus times minus, plus, divided by plus. So you get a plus number. So the sign on this interval has to be plus. Okay. Similarly, you can verify that. Let me write that this is positive. Similarly, you can verify that this number is negative. If you plug in 0 in the function h prime, you will see that that number is going to be negative. And this number is also negative. And this number is going to be positive. What does this mean? H prime of 0 is negative means we have a negative sign in this interval. That means your derivative is negative everywhere on this interval because it is negative for a single value in that interval. Okay. All right. And in this interval here, h prime of 5 is negative. So that means your derivative has to be negative in this entire interval. By the way, at x is equal to 2, your derivative is undefined. Notice that at x is equal to 2, your derivative is undefined. So we write, usually we write, does not exist. DNE, does not exist. And in the last interval, in this interval, your derivative is positive. Now I can use theorem 3.6 to find where my function is increasing and where it is decreasing. By theorem 3.6, let's make sure that the theorem number is correct. By theorem 3.6, h is increasing on -∞, -3. As I told you in the previous example, as a convention, we will be using open intervals from here onwards, okay, to describe decreasing or increasing intervals. -∞, -3, and we have another interval where function is increasing. Notice that function is increasing if your derivative is positive. In this interval, derivative is positive. In this interval also, derivative is positive. And 7, infinity. And then h is decreasing on -3, 2 and 2, 7. In those two intervals, your function is decreasing. Why is it decreasing? Because the derivative is negative on those intervals. Okay. All right, that completes that example. All right, let's move on to our next example. Here is our next example. Oh, pardon me. I want to go over this theorem before I go to next example. Theorem 3.7, functions with the same derivative differ by a constant. Okay, what that means is that if f prime of x is equal to g prime of x for all x in the interval a comma b, then for some constant c, f of x should be equal to g of x plus c. Okay, so in other words, if we have the same derivatives, for two functions, those two functions can differ by a constant. Or in other words, f of x minus g of x has to be equal to a constant. This is nothing but if you move your gx to the left-hand side, you get f of x minus g of x, right? That difference is a constant. That's what it says. Okay. We can quickly prove this theorem. So let's assume that proof. Assume that f prime of x is equal to g prime of x for x in the interval a comma b. Okay. Now I'm going to move my g prime of x to the left-hand side. You get f prime of x minus g prime of x is equal to 0. By the difference formula for derivatives, we have f minus g prime of x is equal to 0. That means the difference f minus the function f minus g, the derivative of the function f minus g is equal to 0. If the derivative of a function is equal to 0 on an interval, that means by theorem 3.6, let's go back to theorem 3.6. If f prime is 0 in the interior of I, then f is a constant on I. Okay, that means, as you can see here, f prime of g, if the derivative of f minus g is 0, that means f of x minus g of x has to be equal to a constant. The derivative of this function is equal to 0, then that function has to be a constant by theorem 3.6. Okay. All right. That means you can, of course, move your g of x to the other side to get the desired result. Plus c as needed. Okay. All right. Let's move on. All right. Next, we have the most important theorem in this section. Okay. This is what we were after so far. Theorem 3.8, the first derivative test. Okay. I will denote it by FDT, first derivative test. Okay. Here is the statement of the theorem. Suppose x is equal to c is the location of a critical point of a function f, and let a comma b be an open interval around c that is contained in the domain of f and does not contain any other critical points of f. If f is continuous on a comma b and differentiable at every point of a comma b except possibly at x is equal to c, then the following statements hold. Okay, let's see what those statements tell you. Here is the first statement. If f prime of x is positive for all x between a and c and negative for x between c and b, then f has a local maximum at x is equal to c. Okay, we can easily understand this intuitively using graphs. Okay, what does this tell you? Let's say your A value is here. This is your A, this is your B. In between, you have the value C. Somewhere between A and B, you have value of C. What does this tell you? F prime is positive for all x between A and C. That means if your x between A and C, F prime is positive. If F prime is positive, shouldn't your graph look like this? If F prime is positive, the slope of the tangent has to be positive everywhere, right? Everywhere on this graph, the slope of the tangent has to be positive. That means your function should be increasing like this on the interval a comma c. That's what we mean by f prime of x is positive for x is between a and c. And then the next, and then it says negative for x between c and b. If your x is between c and b, it is negative. F prime is negative. That means your function should look like this. Your function should be decreasing. Okay. All right. So as you can see, now the combined shape would be a shape of a local maximum, right? Because I told you that in the previous section, if you have a shape like this or like this, it is the shape of a local maximum. As you can see here, you have a local maximum. What do you need to have in order to have a local maximum in this case? Your f prime of x has to be positive in the left interval, in this interval, and it is negative on the other interval, this interval. In that case, that will produce a local maximum. Okay, all right, let's look at the second part. Now it says if f prime of x is negative for x between a and c and positive for x between c and b, then I will shift this little bit upward like this. F prime of x is negative for x between a and c and positive for x between c and b, then f has a local minimum at x is equal to c. Again, we can clearly see this if you draw a picture. This is your A, this is your B, say this is your C. Okay. Then between A and C, your f prime of x is negative. That means your graph has to look like this. And then for x between C and B, that means for x between in this interval, for x in this interval, your derivative is positive. So it should look like this. As you can see, you have a local minimum, the shape of the local minimum at x is equal to c. Okay, and let's see what the third part says. If f prime of x is positive for both x between a and c and x between c and b, then f does not have a local extremum at x is equal to c. This is again very obvious if you draw a graph, a situation like this. Okay, this is your interval A and B. Think about a situation like this. Okay, you have a situation like this. This is your point C. As you can see here, the derivative is positive. Derivative is positive for x between A and C because it's increasing. The derivative is positive. And after C, in the interval C comma B, again the derivative is positive. In that case, we don't have a local maximum or a local minimum. It's clear. You don't have this shape or this shape there, or constant shape. Okay, so you don't have a local extreme. Okay, the fourth case is very similar to this case. In that case, f prime of x, if f prime of x is negative for both x between a and c and x between c and b, then f does not have a local extreme. Okay, a graph like this would be appropriate for that case. We have a and b. You have a case like this. Okay, in both intervals, your function is decreasing. Okay, here is your value C. Here is the value C. As you can see, in this case also, you do not have a local maximum or a local minimum. That means you don't have a local extrema at x is equal to C, because in both sides, the derivative is negative. Derivative of your function is negative. All right, let's move on. That's what the first derivative test tells you. Okay, now let's work on this example. Okay. Let f be a function whose derivative f prime has the signs indicated on the sign chart shown. This is the sign chart given to you. And here we use a convention, that is, if there is nothing written on top of a number, like for example, -1 is marked here, but there is nothing written on here. That means the derivative is 0 at this point. That is a convention that we use. Okay. If the derivative does not exist, on right top of that number, you write DNE. That means does not exist. Or in other words, your derivative at x is equal to 2 does not exist. Here, the derivative at x is equal to -1 is equal to 0. Okay, if there is nothing written, the derivative is 0. Okay, all right, let's see what the question asks us to do. Use the sign chart to sketch possible graphs for f and f prime. How do you draw a possible graph of f? Let's first do the possible graph of f. How can we draw a possible graph of f in this case? Notice that in this entire interval, your derivative is positive. Let's first of all have our x and y axis. This is your y-axis. This is your x-axis, or you would say f of x is equal, y is equal to f of x. Okay. All right, I know that in this entire interval, my derivative is positive. The sign chart for the derivative is given, derivative is positive. Derivative is positive means my function is increasing, right? We know that. So this is -1. From negative infinity to -1, derivative is positive. That means you should have a shape like this. At -1, my derivative is 0. That means the tangent at x is equal to 1 should be horizontal. So you should have a shape like this, a peak there. And then between -1 and 2, the derivative is negative. That means your function should be decreasing. I'm not drawing this to a scale, okay? Okay, between -1 and 2, my derivative is negative. That means my function is decreasing like this. I'll use screen. My function is decreasing. Notice that at x is equal to 2, my derivative does not exist. Derivative does not exist means I can do several things here. Either I can have an infinite discontinuity here, or some sort of discontinuity, or I can make this a sharp corner. We know that at sharp corners, my function is not differentiable. So at this case, in this case, at x is equal to 2, it is not differentiable because we have a sharp corner. Why did I decide to go this way? Well, I know that between 2 and positive infinity, my derivative is positive. Derivative is positive means my function should be increasing like this. So that's why this is going up. Okay, this is a possible graph of f. All right, now how do I draw a possible graph for f prime? Yeah, if you look at this sign chart, f prime is positive in this interval. That means you would have a shape like this. Because your f prime is, this is the graph of y is equal to f prime of x, okay? I'm going to draw the graph of y is equal to f prime of x on this plane. Between minus infinity and minus 1, your f prime is positive. That means it should lie above the x-axis. So it should be a graph like this. At minus 1, it is 0. I know that the derivative is 0 at this point. And then between minus 1 and 2, it is negative. Derivative is negative. So you would have a shape like this. And notice that at x is equal to t2, your f prime is not defined. That means I'm going to have something like this. Okay, at this point, it is not defined. And notice that in the interval 2, infinity, your f prime is positive. Positive means above the x-axis. So I will draw it like this. This is a possible graph. Okay, if you look at the book has drawn like this. Either way is fine. Okay, because there can be a lot of possible graphs for this case. Okay, as you can see, at x is equal to 2, your function is not defined. Here you have an open circle. Here also you have an open circle. So it's not defined at x is equal to 2. In this interval, your function is positive. Because of this, I want my f prime to be positive. And on this interval, it is negative. Of course, it is negative because it lies below the x-axis between minus 1 and 2. That's what I want. And at 2, it is not defined. And beyond 2, it is positive. F prime is positive. It lies above the x-axis. Okay, so that's the possible graph. All right, that completes that example. Let's move on to the next example. All right, here is the example where we are going to use the first derivative test. Okay. Sketch the graph of each of the given functions. Along the way, determine all local extrema and important features of the graph. Okay. All right, let's work on the first part. We are given the function x cubed minus 3x plus 2. We need to sketch the graph of this one. What I'm going to do is, again, I'm going to construct a Sine chart for my f prime of x. I want to know in which interval my f prime of x is positive and in which interval my f prime of x is negative. Okay, my goal is to apply the first derivative test to locate the local maximum and local minimum. All right. So if you look at this function, you can see that the derivative f prime of x is going to be 3x squared minus 3. Now we can find, we need to find the intervals where f prime of x is positive and the intervals where f prime of x is negative. For that, I'm going to construct a Sine chart for f prime of x. Okay. So this f prime of x can change the sign only at its zeros, because as you can see, this is a polynomial. So there is no discontinuities or there are no points where the function is not defined. So this can only change the sign at its zeros. So let me find the zeros of this function f prime of x. I set my 3x squared minus 3 to 0. That will give you 3x squared is equal to 3. Then you get x squared is equal to 1 by dividing both sides by 3. That means x is equal to plus or minus 1. So these are the zeros of your derivative function. That means your derivative is 0 at each of these points, at -1 and at +1. All right, now let me complete the Sine chart here. Here is your 1, -1, and here is your +1. Okay. Now I'm going to figure out the sign in each interval. I'm going to compute f prime of -2 and then f prime of 0. I'm picking 0 from this interval and I'm picking -2 from this interval. And from the last interval, I'll pick 2. And if I compute these values, you can easily verify that f prime of -2 is +9. That means it is a positive number. And f prime of 0 is -3. That means it's negative. F prime of 2, this should be prime, by the way, should be positive. Okay, so that means I can put the sign here. On this interval, your derivative has to be positive. And on this interval, your derivative is negative. And in the last interval, your derivative is positive again. Notice that in this interval, your derivative is positive means your function should be increasing. So your shape should be like this. It would be like this or like this, but I will just draw a straight line. It's an increasing function. And on this interval, your derivative is negative. So shape should be like this. And in this interval, shape should be like that. I can draw the rough shape. I'll use red color like this. In this interval, it should be like this. In the last interval, it should be like this. We have a rough shape of the graph. Now, intuitively thinking, you will have a shape like this. But let's use the first derivative test to verify this. Okay. Notice that my function is continuous at x is equal to -1. This is a polynomial. It's continuous everywhere. Not only continuous, it's differentiable everywhere. Okay. So I can apply the first derivative test. Okay. By the first derivative test, since my derivative is positive to the left of -1 and it is negative to the right of -1, and my function is continuous at x is equal to -1, I should have a local maximum at x is equal to -1. Actually, these two lines suggest the shape, these two lines suggest that I'm going to have a local maximum, because if you kind of connect these two, as you can see, you're going to have a local maximum. Okay, by first derivative test, we determine that by first derivative test, f has a local maximum at x is equal to -1. Again, by the first derivative test, notice that if you look at this point, in this interval, your derivative is negative. In this interval, your derivative is positive. At x is equal to 1, your function is continuous. So we can apply the first derivative test to conclude that we are going to have a local minimum at x is equal to 1. And f has a local minimum at x is equal to 1. Okay. Another thing that we can do before we graph it is that we can find the function value at x is equal to 1. I know that there is a local maximum at x is equal to -1. I can find that maximum y value. I can plug in this x is equal to -1 in my function to find the maximum value. So here I have done that calculation. F of -1 is equal to 4. Similarly, I can find the minimum value at x is equal to 1. I can plug in this x is equal to 1 in my function to find the minimum value. If you plug in x is equal to 1 in your function, you will get 0. Okay. Now we are ready to go for the graph. Let me graph my function now. This is -1. This is +1. And I know that at x is equal to -1, I'm going to have a local maximum by first derivative test. The local maximum value is 4. At x is equal to -1, y value is 4. Okay, so I'll mark that point here. Let's say this value is 4. So that means I'm going to have a shape like this at this point. I need to figure out the rest. We will figure that out. And then at x is equal to 1, I'm going to have a minimum by the first derivative test again. At x is equal to 1, my y value is 0. So that means here is the minimum value. So your graph should look like this. This will be going up forever, and then this will come and go down like this. Okay, so this is a rough sketch of the graph of f of x. Okay. Finally, you could write, we know that the local maximum occurs at x is equal to -1 and the maximum value is 4. So we have a local maximum of 4 occurs at x is equal to -1, and local minimum of 0 occurs at x is equal to +1. This should be +1, by the way. All right, this completes the first part that I want to go over. Okay, we need to sketch the graph of this one. Again, the idea is same. I want to have a sign chart for the derivative of this function because I want to identify local maximum and local minimum. I can use the first derivative test to identify local maximum and local minimum. Okay. All right, let's go over this example. First thing I'm going to do is I'm going to calculate my derivative, f prime of x. For this function, if you calculate the derivative, you can see that it is going to be this particular function. Now I want to construct a sign chart for the derivative function. Okay. So first I'm going to find the zeros of this function f prime, zeros of f prime. I'm going to set my numerator to 0 to find zeros. First of all, notice that there are no common terms to cancel. Okay. So I set my numerator to 0 to find the zeros. You get x is equal to 0. And then notice that function is discontinuous. We have an infinite discontinuity at x is equal to 1 because at x, when x is equal to 1, your denominator is 0. Discontinuity of my f prime. How do I find that? You set your denominator to 0. Is equal to 0. This means x has to be equal to 1. So that's what I want for my sign chart. Now I am ready to go with the sign chart. I mark these two numbers. I mark the 0, which is 0, and the point where my function is discontinuous. Function f prime, okay? I'm looking at the function f prime, not the function f, okay? I'm going to construct the sign chart for f prime. This is the number 1. Now I'm going to find the sign in each interval. From this interval, I will pick -1 from this interval. And from the middle interval, I'll pick 0.5. And from the last interval, I'll pick 2. Now let me compute this. Recall that we only need the sign of this number. If you compute this number, you will see that it's going to be a negative number. And if you compute this one by plugging 0.5, pardon me, this should be f prime, okay? This should be f prime, this should be f prime. If you compute f prime of 0.5 by plugging 0.5 here, you will see that that's going to be a number bigger than 0. Here again, f prime of 2 is a number which is less than 0. If you plug in x is equal to 2 here, you will see that. Okay. So my sign chart, I can complete my sign chart. Here, the sign is negative. In this interval, sign is positive. And this interval, in this interval, sign is negative. And notice that at x is equal to 1, your derivative is not defined because at x, when x is equal to 1, your denominator is 0. So here you have to write does not exist. Does not exist. Okay, that's the sign chart. And notice that at this point, the derivative is 0. Okay, because 0 is the 0 of this function. Okay, now I can use the first derivative test, f dt. Okay, by f dt, I can conclude that here at x is equal to 1, I'm going to have a minimum, local minimum. Why is that? Because the derivative is negative in this side means your function should look like this. Here it is positive, your function should look like that. And then here it is negative in that region. So your function would look like this. Okay, I don't know whether it is like this here or not. Okay, actually it is not because at x is equal to 1, the derivative is not defined. So it cannot have a shape like this. Who knows? It could be like this, like this. Okay, let's figure that out. Okay. All right. First of all, I can apply the first derivative test here because you have derivative is negative to the left of that point and derivative is positive to the right of that point. That means I should have a local minimum at x is equal to 1 by first derivative test f as a local minimum at x is equal to 0. Okay, we have a local minimum at x is equal to 0. And then notice that your function value, I have copied the stuff to the other side here, your function value f of 0 at 0 is equal to 0. It's clear. If you plug in 0 here, 0. Okay, so that means at x is equal to 0, your function value is also 0. So you would have a shape like this, roughly speaking. Okay, I need to complete the other part. That's a different story. Okay, now let's try to figure out some more details about this graph. Okay, next thing I want to figure out is, am I going to have any horizontal asymptotes in this case? Clearly, yes, right? If you look at this function, degree of the top is equal to the degree of the bottom. So the horizontal asymptote is 1 over 1, right? The coefficient of x squared is 1. The coefficient of the x squared in the bottom is also 1. So the horizontal asymptote is going to be horizontal asymptote is y is equal to 1. I know that y is equal to 1 is a horizontal asymptote. Okay. All right, now let's explore what's happening near x is equal to 1. If you look at this function, f of x, I can write this function as x squared divided by x minus 1 whole thing squared. Notice that x squared minus 2x plus 1 is same thing as x minus 1 whole thing squared. Now, clearly, x is equal to 1 is a vertical asymptote. X is equal to 1 is a vertical asymptote of this function, right? So we need to figure out the behavior near x is equal to 1. First of all, let me have a rough sketch, at least the xy plane setup for my graph. Y is equal to f of x. Here is your 0 and here is your 1. Okay, and I know that y is equal to 1 is a horizontal asymptote. Let's say this is y is equal to 1. This point is 1. And at x is equal to 1, I have a vertical asymptote. I know that by looking at the function, because if you set your denominator 0, you get x is equal to 1. That will give you a vertical asymptote. What happens as x approaches to 1 from the left-hand side and from the right-hand side? Doesn't matter what side your x approaches to 1. For example, let's compute the left limit. Limit x approaches to 1 from the left-hand side, f of x. That clearly takes the form 1 over 0 plus, because as x approaches to 1, this becomes 1, and this approaches to 0 from the positive side because of this square. It's always a positive quantity. So you take the form 1 over 0 plus. That means the answer is plus infinity. Similarly, limit as x approaches to 1 from the positive side or from the right-hand side, f of x again takes the form 1 over 0 plus, that is plus infinity. That means as x approaches to 1, your graph should look like this. From the left-hand side, it will be going to infinity like this, plus infinity, because this is plus infinity. From the right-hand side also, it will be going to infinity like this. So now we can complete the graph, okay? And notice that according to the sine chart, in this interval, your derivative has to be negative. Okay, that means in this interval, derivative is negative. And also I know that here is where my minimum occurs. By first derivative test, I know that at x is equal to c, I have a minimum. Okay, so my graph should look like this. This is my horizontal asymptote. Here is my minimum. Here the derivative is also 0. And then this is a vertical asymptote. I'm not done yet. Maybe I'll make it a little bit smoother so that we can see the derivative at that point is 0. Okay, now it looks good. And then on the right hand side of 1, you have a situation like this. I know that y is equal to 1 is a horizontal asymptote. So your graph should look like this. When x approaches to a 1 from either side, your function value should be going to infinity. That's why you have a behavior like this near this vertical asymptote. Okay. Now we have taken all the properties into account. We have a local minimum at this point. By the first derivative test, we determine that we have a local minimum at that point. The minimum value is f of 0 is equal to 0. So this is the minimum value. You should have a shape like this. In this entire interval, the derivative is positive. That means your function is increasing. And in this entire interval, your derivative is negative. Your function is decreasing, as you can see. And in this entire interval, your derivative is negative. Your function is decreasing. Okay, so this is a rough sketch of the graph of the given function. Okay, all right, that completes the proof. Actually, we can write the minimum value. Minimum of f occurs at x is equal to 0. The minimum value is again 0, because minimum value means the y value at x is 0. Okay. All right. That's all I wanted to talk about for this section. I'll stop there and I'll see you next time.